All right, AP Chem Squad, we are on the last video. This is going to be a little bit longer. Just make sure you guys can recall the Hess law. And I hope you all are doing the problems and asking any questions in class if you're not clear about it. So let's dive into our last topic of this chapter. All right, so in this section, we are going to have a lot of new vocabulary words that you would be coming across. Think about the Hess law that we had done in our unit 3. So we are going to describe the reaction mechanism. Remember, we had talked about kinetics, and what kinetics looks into is the pathway or the reactant changing into the product. So we are going to look at the reaction mechanism. Describe the elementary steps for a mechanism. We'll identify an intermediate in an elementary step. We'll be able to identify a catalyst and predict the rate law for a region given a simple mechanism, and identify the rate determining step. Okay, so a lot of small little topics. So make sure you are sitting in a quiet place and taking notes. So this will help us look at the reaction in terms of at a microscopic level and see what is happening at the level that we are not able to see. And how a reaction proceed is given by its reaction mechanism. So what are some of the postulates of a mechanism is measures the rate of reaction, formulates the rate law, and postulates a reasonable reaction mechanism. So we are going to see how different steps can be related to the rate law of the equation. So important terms are the elementary steps, rate determining steps, intermediate. So what is an elementary step? Occurs as a single event. Rate determining step is the slowest step in the sequence, very important. So the rate determining step is the slowest step in a reaction. Intermediate, it is a species first formed and then consumed later on. So we will work on how we can identify these different parts in a reaction mechanism. So what is a mechanism comprised of? It is comprised of series of elementary steps. You add all the elementary steps to get your overall reaction in a correct stoichiometric ratio, and rate law is determined from the experiment. So rate law can be determined from an elementary steps known as elementary step. So if they tell you that this is an elementary step, very, very important. We do not need an experimental data, but what is the important word? If it is an elementary step of a reaction, you can write down the rate law, and in this case, the order of the reaction is the stoichiometry of the reactants. Over here, if this is your second equation and it is your elementary step, you could write the rate law as rate constant times the concentration of the reactant. Because the coefficient is a 2, you can write down 2, provided they have said that it is an elementary step. So read carefully. A series of elementary steps, rate determining step, the slowest step in a multi-step mechanism, sum of the overall reaction stoichiometry. I will just use the word RDS for the rate determining. Think about what is our rate determining step to get to school. It is usually when we are making a turn on the Walnut Street, right? If you are stuck over there at 8:15, you're going to be late for the class. But if you're there by 8 o'clock, you can make it. So there is always some point in your journey that determines how fast you're going. What this is showing, these are your different reactions. So these are your different elementary steps of a reaction, 1, 2, and 3. You add all your reactants, you write down all your products, you cancel out everything that is common on both the sides. So if you remove this and, 2A, A2, this cancels out over here. And if you look at it, this becomes your net equation, like what we were doing. So this is your net equation with a correct stoichiometry ratio. If these are your elementary steps, what this is saying you can use this to write your rate law, where coefficient determined is the order of the reactions, provided they are your elementary steps. Now, if you look at this reaction, what is an intermediate? Intermediate are the species that appear in a reaction mechanism, but not in an overall balanced equation, because an intermediate is always formed in an earlier elementary step and it is consumed in a later elementary step. So if you look at a reaction in your elementary step, and there is a molecule that is there in your product, but now it is in your reactant and you do not see it, therefore we would say that this is your intermediate. So intermediate is something that is present in one step, but it is consumed in the other step, and you will not see it in your overall reaction. That is how you'll be able to identify your intermediate. The other important thing is the molecularity of a reaction. Unimolecular, just elementary step only has one molecule. Bimolecular, if the elementary step has two. Termolecular, if they have more than 3 molecules. So if you look at these all are your bimolecular because you have 2 reactants in your elementary step. Now, if you're looking at this, the rate of the overall reaction can never be faster than the slowest step. So in this case, they are saying step 1 is the slowest step in the mechanism. In reaction 1 is the slowest step of the 3 step, then it is known as the rate determining step. So the slowest step, and they will give it to you, and later we'll show you how we will identify which one is the slowest step by looking at the activation energy graph. Just a lot of new vocabulary words. The slowest step controls the rate of reaction. It also determines the rate law for the reaction. So what will be the rate law for this reaction is going to be, because this is your slowest step, the overall rate for this equation is going to be KAB, because that is your slowest. The rate law is not based on the overall reaction. All right, so now the rate of this reaction, you cannot say this. The rate law is not based on the overall reaction. It is based on the slowest step. Again, these are all your elementary steps. For each elementary step has its own rate law. Okay, so make sure we are able to comprehend and understand what I'm trying to say over here. So if they have given you this equation, and if you look that they are given this equation, they're telling you that the rate is KNO2. So that means it is first order with respect to nitrogen dioxide and first order with respect to fluorine. Explain the observed kinetics as possible mechanism, right? So they have given you over here, this is your slowest step. If you look over here as per the slowest step, you can say that this makes sense, that this is your rate law for this equation. This is your fastest step. This is your overall reaction. So if they gave you this, you will be able to write down the rate law based on the elementary steps that they have given. Now, if you look at this equation, since the first step in the reaction is the slowest step, it determines the kinetics and the rate law of the equation. Validating a reaction mechanism. The individual elementary step must sum to yield the overall reaction and a correct stoichiometry. The predicted reaction rate law must be in agreement with the experimental determined rate law. So, right, if you collect our experimental rate law, they both should be same. Note there may be more than one mechanism that is in agreement with the reaction stoichiometry and progress of a chemical reaction. Here are your elementary steps. Now, if you look over here, since we have this and we have this that is being used up in both the steps, I hope you all can remember the word. We will call that this is your intermediate, and you can get the overall reaction. Once again, this is talking about that this is your unimolecular reaction. If these are your elementary steps, these will become your rate law. This is your bimolecular reaction. The sum of the elementary step must give the overall reaction. I know it is a repeated slide, but I hope this helps you just look at it one more time. And the rate determining step is the slowest step in the sequence. So this is what we have talked about so far. Now, the reaction rate is controlled by the rate determining step. Now, what is that rate determining step, the slowest step? It is going to be based on the activation energy that you're looking at it. Whenever a fast step precedes a slow step, solve the concentration of the intermediate by assuming the equilibrium is established in the fast step. Okay, so we are going to look at this equation, but at this point, I want you to make sure you make a note of this. And equilibrium is achieved in the fast step. Why this is going to be a fast step? Because the activation energy is smaller. Here, if you're looking, the activation energy is much higher. Therefore, this is what is going to be your rate determining step. Steps after the rate determining step do not affect the rate law. So step 3 is not going to affect your rate law. Okay, so this step is going to reach an equilibrium. This is going to be a slowest step because of the highest activation energy. All right, what is the equation for the overall reaction? So now if you're looking at this equation, the experimental rate law for the reaction between NO2 and CO to produce NO and CO2 is this. So they have given you the rate law. The reaction is believed to occur by these two steps. Okay, so now if we cancel, therefore, now if you look at this, what are we going to do over here? NO3 is going to be called your intermediate. Now, if you look over here, NO2 is in your reactant and it was in your product. We will call that, later on we'll look at it, that is your catalyst. Catalyst is something that is present at the start of the reaction and it is also there at the end of the reaction. That is your catalyst. We are going to look at it. So what is an intermediate? I hope you all identified NO3 as an intermediate. What can we say about the relative rates of the step 1 and 2? So if this is telling you K is NO2 is the rate law for step 1, so step 1 must be the slower step than step 2. Because they already gave you this and they have given you this equation, because they told you that is your rate law, you can predict that step 1 is your slower step. And you can also say that between this, that step 1 would have a much higher activation energy. Yeah. So take a minute, pause, and try to understand everything on this slide that I just went over. So what is an equilibrium? Some reactions are reversible. We use a double arrow to indicate that. And equilibrium is the rate of the forward reaction is equal to the rate of the reverse reaction. This is important right now. We will build a lot more later on. It is common for catalysts to show up in rate expression. This is not a problem since the scientists added the catalyst to speed up the reaction. Right. So we talked about elimination of the intermediate. All right, so let's try to understand how we are going to eliminate an intermediate in a rate expression. So if you look at this equation, you are given the two elementary steps. Your slow step is your rate determining step. As a result, you can come up with a rate law and you would say that the step 2, therefore the rate law is going to be K2 NOCl2NO. But now the problem over here is this NOCl2 is your intermediate, correct? Because what it is saying is that intermediate can never be part of your rate law. So how are we going to eliminate this intermediate from your rate law equation? All right, so what you will do is, now remember I told you the step before the slow step, which is your fast step, is in an equilibrium. If it is an equilibrium, we can say that the rate of NOCl2 is equal to the rate of NOCl, right? Because it is at an equilibrium. Now, if we know this, these are your rate constant K1 and K minus 1. Now, since this is your intermediate, you manipulate the equation to solve for NOCl2. Now, if you do that, you will get NOCl2. If you substitute this, this is what we are getting. Now, K1, these are your constant, right? So we can just call it as our new constant, and all these constants, and K2 is your constant. We kind of can get rid of all of these, and we can call this as a new constant K. Now, where did we get this? Because we substituted this NOCl2 that we got over here into this equation. So if you plug in, you're getting rid of the intermediate, correct? So if you get rid of the intermediate and you plug in this value, this is what it is, NO2 and NO2. So therefore, you're getting 2 over here and Cl2. So what this is telling you, this is your overall reaction, and now it is second order with respect to NO and first order with respect to chlorine. There is similar problem in your packet. Please pause and solve this problem. So the important point over here was intermediate cannot be in your rate law equation. If it is there, you would have to look at the previous equation, manipulate the equation for the intermediate and substitute the new values that you get. Here, this problem over here, they have given you, this is very common thing, which is easy. Most of you do a good job. You should be able to identify your intermediates. You should be able to identify the catalyst. So I hope you are looking at this and it is making sense that this is your catalyst, because catalyst is something that speeds up the reaction without being consumed, while intermediate is something that is there in your product and then it is consumed in the next step. So this one is here. Now we are here on our last part of this chapter, which is describe the function of what a catalyst does. So what does a catalyst do? It lowers the activation energy, proceeds by a different mechanism. It takes an alternate pathway. A catalyst is something that is not consumed. Overall stoichiometry is unchanged. It does not change the stoichiometry ratio. What it does is it lowers the activation energy. That is the most important part. And also the enthalpy of the reaction does not change, right? The delta H, the difference between the energy of the product and the reactant remain the same. So this is important conceptually, what a catalyst does. Now, if you look at this graph, what a catalyst is doing, it is creating a new mechanism. You have a much higher activation energy. It will create multi-step reaction, and that is what a catalyst is doing. So a catalyst increases the rate constant, formation of more stable activated complex, increases collision of the molecules, improved orientation of the molecule. So catalyst is helping all these things. As a result, it speeds up the reaction. And as a result, a catalyst often results in a new mechanism. Mechanism is changed, activation energy is changed, but enthalpy of the reaction is. A catalyst is a substance that increases the rate in a chemical reaction without itself being consumed. So this is what we were talking about. Remember, as per the Arrhenius equation, if this is your original pathway, once you use a catalyst, it is lowering the activation energy. I want you to pay attention over here. The energy of the reactant and the energy of the product does not change. Catalyst only affects the activation energy. And it lowers the activation energy for a forward reaction as well as for the reverse reaction. So this is an activation energy for the forward reaction. This is the activation energy for the reverse. If this reaction is given, mechanism has 3 steps. So if this graph was given to you, I think so I just did a little bit sooner. If this is what is given, the mechanism has 3 steps, so needs 3 activation energy. The first step is the slowest step, so needs it has the highest activation energy. All 3 steps are exothermic, so the potential energy value for the intermediate product are lower. The potential energy for the product is lower than the reactant, showing the reactant is overall exothermic. Okay, so if they give you a equation, you should be able to draw the graph for that. Stop the video and sketch the reaction profile for the mechanism. Or they can give you the graph and you should be able to identify which one is going to be the slowest step and which one is going to be the fastest step. So it can go either way. So this is from our AP classroom. And to make sure you have done all the flip problems, here is a joke of the day. In a sports relay race, a chemical kinetics specialist runs slowly and his group loses the race. When the chemical kinetic specialist is asked why he ran slowly, his reply was, I always wanted to be significant rate determining step. Here is something more. What does this look like? It looks like a plain hat. You are an adult. It looks like an elephant eaten by a bull. You are still a child at heart. But if you look at this and you say it looks like that first step over here has a much higher activation energy than the second one, therefore this is the rate determining step. You have mastered the topic of chapter 14 and you guys are doing amazing. Proud of you. Keep up the good work and ask us any questions that you might have. Enjoy doing your problems. Bye-bye.